to have. It's a tremendous pleasure to have Konrad Waldorf of Universität Greifswald here with us. For me, the pleasure is to introducing Konrad is twofold. On the one hand, Konrad is an expert in high geometry and high gauge theory. You will find out what this means in the course of this lecture, I suppose. Who's been developing this rapidly growing field of mathematical physics and physical mathematics for the last, Konrad, almost 20 years, I counted it. And the reason I have this good estimate of the number of years he's been in a field is because our acquaintance goes as far, almost 20 years back to the time when Konrad came to Lyon, to Gawęcki, from Schweigert's group, to learn and then also to teach Krzysztof and myself, gerbes, gerbe theory, a la Marian Stevenson, and later to collaborate with us, something that I reminisce with respect and pleasure. So today we have Konrad, who's going to introduce us to a rather nice structure, which arose early on in loop mechanics. People realized that loop mechanics on topologically, differential geometrically, vastly, and metrically vastly inequivalent geometries, toroidal bundles. Loop mechanics is, roughly speaking, the same in duality. Loop mechanics in toroidal backgrounds, metric and with, as Konrad is about to tell us, with gerbe on top of it. So this is generally speaking the physical background to it, and Konrad is going to walk us gently through this field. So please, Konrad, the floor is yours.
Hey, thank you, Raphael, for these kind words, and thank you for everybody for having me. Yeah, it's indeed a pleasure to think back to these times 20 years ago in Lyon, when Raphael, Christoph, and I were working on sigma models and gerbes and developing all this from like very basic grounds to fully fledged theories that we have available now. And yeah, so today I would like to talk about like an application, if you want, of this right now fairly high developed gerbe geometry to a very interesting physical situation, namely the situation that two string theories are dual and to each other in a sense, and the sense is exactly given by these Buscher rules. So the first point here would be to show you the Buscher rules. So they are here on this little black field, and you'll see that they are quite involved. So these are the Buscher rules, and they relate two things to each other, namely pairs GB, or one pair GB to another pair GB. So what are these GBs in the first place? So here we're talking about string theories on some target space, so classical formulation of string theory. And so the G, that's a little metric on the target space, and the B is a B field. And here I'm thinking about B fields as just being two forms on the manifold. So G and B live on some manifold. And so that's like, in a very basic sense, the background fields for string theory. So I suppose you have more or less heard about this already. So let me just sketch what these fields are good for. So if we have a string say a closed thing that sort of travels through the manifold M. So while it travels, it sweeps out a surface. In the simplest case, looks like a cylinder, but also some more complicated surfaces can occur like this. So So coupling such string to some background fields involves these two-dimensional surfaces, these world sheets sigma. And now there is the metric on the manifold is used to formulate the classical kinetic term for such a thing. So if the trajectory of the string is parameterized by a map from sigma to the manifold, then there is a kinetic term. So which looks like some derivative of, is a quadratic term in the derivative of phi. Let's put it like this. And in order to do the norm, we need the metric on the manifold and also a metric on this world sheet, which is not so relevant today. And so that's the usual kinetic term. And the B field is used to construct a coupling term, which is simply obtained by integrating B, it's a two form, over the two-dimensional surface, so rather the pullback B along phi over the surface. So that's another number, and this makes up the action functional for the string. So that's how these two things, G and B, are used in order to define a string theory. And now here the Buscher rules do this or relate like one of these string theories to another configuration, G hat, B hat. So the Buscher rules do not relate like arbitrary string theories to arbitrary other string theories. Here there is a condition imposed on the manifold, the background manifold M, namely, as Raphael already announced, that we look at target spaces, manifolds with a toroidal symmetry. And this means in the simple situation, and that's the one that I want to look at here first. So let me make this explanation smaller. The simple situation is where this manifold M has just the structure of some Euclidean space times some torus. The simplest example of a toroidal manifold, a torus bundle, which is just a direct product. It's a trivial bundle. And that's also true on the other side. So in that sense here, the dual space, target space, is also the same. Okay. And now if the manifold is a direct product of two manifolds, then metric and B field can be like written in components with respect to this product structure. So this looks like as follows. So G, with respect to this product structure, is a 2x2 matrix of a metric Gij on the first factor, Rs, and a metric G mu nu on the second factor, Tn, and like here off-diagonal components, which I might or might not, like maybe write like this. I don't know what a good notation for this is. So the entry here sort of doesn't matter so much because it's a matrix, so it's symmetric. So this matrix is symmetric, and everything what's here is like transposed of this. So let's ignore that. And similarly, now erase this. The B field is also split into components: Bij, B mu nu, and Bi mu. And here is like Bi mu transpose, because the metric is a two form and it's anti-symmetric. So here it's understood that the I and J, so Latin coordinates, are running from 1 to S. That's the dimension of the first factor. And the Greek coordinates run from 1 to N, which is the torus dimension. And then sort of these equations here, the Buscher rules, sort of start making sense. So the first, so the Gij, the Ij part of the G hat metric on the right-hand side is given by this formula. So this is an S by S matrix. This is an S by S matrix. And then sort of this product of like vectors makes sense. So this means the inverse matrix and the element at mu nu and so on. So one can sort of give sense to these rules. So of course, these Buscher rules sort of look complicated, and it's not clear at all why they are like this and what they mean. And I also don't want to try to give much sense to them now. The only thing that's very important to notice here is that the Buscher rules mix the G and the B components up. So you see that the dual metric G hat on the dual side, Gij, it involves also B field components, and vice versa. The dual B field involves metric components. So metric and B field do not transform under T-duality, do not transform like separately, but they get mixed in a very intriguous way. Any questions?
May I ask a stupid question?
Sure.
Suppose G and B combine into Kahle structure. What is the trace of this structure on the dual component?
So sorry, didn't understand. Say again. Combine into what?
G and B into Kahle structure on M. Special data. Yeah?
G and B.
A two form and the metric may be sometimes combined into Kahle structure on a manifold.
Oh,
They have fulfill some equations. And then what is the trace of this Kahle structure on the dual space? So it is also Kahle, perhaps not. But why Kahle?
Did you say Kahle? I don't understand why that should be Kahle. The metric is just Riemannian metric here. And a priori, like on this side, there is no relation between G and B. They can be like chosen independently. Only on the dual.
This I understand.
Yeah.
Okay.
So this looks like a type of Kaluza-Klein approach, yes? And the G is a metric on the total space of the principal value. And what is B?
Exactly. We'll come to this in a second. This is exactly like a Kaluza-Klein situation.
Maybe just a small comment, Konrad, referring back to Jacek's question. So it's not exact, since we're talking about string theory or loop mechanics, it's a two-dimensional field theory with classical conformal symmetry, and sometimes you want to preserve this conformal symmetry, which means that you want to kill the so-called conformal anomaly in the quantum regime. This imposes actually some constraints on G and B. They're not independent. And in fact, they can the condition can be succinctly expressed as saying that if you think of dB as the torsion tensor on the metric manifold with G as the metric, then you have a Weizenburg connection. So with the Ricci tensor, flat Ricci tensor for the Weizenburg connection containing the torsion given by dB. So that really consider it as a three-form giving the torsion tensor. So they are related, but not they cannot be taken arbitrarily. That's my point. Not quite.
I see. Okay.
They form a Weizenburg pair.
So this goes into the direction of what I've wrote here, namely that Buscher compared the quantum field theories on both sides. So he needs to quantize these things and probably encounters the scalar condition for the well-definedness of the sigma model. Yeah, that's correct. So I'm kind of neglecting this here because I'm only dealing with the classical sigma model, the target space geometry of the model. But of course, it is important to have in mind that we have these quantum field theories associated to sigma models because that's the main motivation for these equations. And Buscher showed this in like in surprisingly simple calculation actually in his paper, that the two sigma models on this that are dual in the sense have determined the same quantum field theory in that sense.
So if I may make a remark, so a Kahle condition will only appear if you consider a supersymmetric sigma model. And if you want to preserve a certain amount of supersymmetry in the uncomplexified directions, this RS. So here, as far as I understand, you are only assuming, you are only assuming a bosonic sigma model, so you won't have a Kahle condition.
Yes.
But as it was pointed out before by Rafal, what you can impose is the conformal anomaly, well, conformality condition. So you can require a vanishing of beta function at one loop in order to ensure conformality, and that will give you the condition that he mentioned.
Yeah,
so
that's correct.
Two different issues that got mixed.
Right. So here I'm just looking at the bosonic sigma model, as you said, yes.
Maybe I can also make a remark as a tour. I just wanted to say, I mean, this is a good question with this Kahle, but if B is not just closed but exact, then it's just a boundary term and you can just put it away. So actually, to be closed or exact is actually a bad idea. This is like in the kernel of the whole consideration in some sense. So that's all.
Yeah, B is typically not closed here because we soon want to consider the H flux of the B field and we don't want it to be zero.
Yes.
Right. Okay. So let's yeah, it's true. So from this point of view of quantization and actual quantum field theories, what I'm doing here is like very naive. I just consider the classical data and analyze it mathematically as far as I get, without performing any quantization. So I wanted to come to this important point that sparked the interest of mathematicians in T-duality, in particular called topology change. So what is topology change doing here? And what topology is changed? So the point is that as soon as we talk about sigma models, we are interested in target spaces that do not have this trivial topology of just Euclidean space times the torus, but rather we are interested in fairly arbitrary topologies, which then, because we need this toroidal symmetry, are supposed to be torus bundles over X. And as you know, this is like a very familiar situation for string theorists that space-time is compactified on a torus. And now the question is, if I have now such arbitrary torus bundle and want to apply the Buscher rules, what do I get? And this question has been posed by these people here. And of course, the obvious idea is, well, we can locally trivialize torus bundles, bringing us locally back into this situation, then apply locally the Buscher rules and try to glue the dual things together. So let me sketch this. So this means we take an arbitrary torus bundle equipped with Riemannian metric and B field, and then look at it locally. So we restrict to some, say, open set U alpha of the base manifold. So M is a torus bundle of X. U alpha is an open set in X. And if we have such local trivialization, then we are back in the old situation, and get a metric and a B field, but depending on this chosen coordinate patch, U alpha, okay, but never mind. So then we can apply the Buscher rules to that. And the Buscher rules just determine by these equations dual metric and dual B field. And then we can try, or at least that could be the idea, to glue these local patches together to get a new metric, G hat on M and B hat. And then it was like noticed in this paper by Alvarez and colleagues that this gluing doesn't work. So simply the local data for metric and two form that I get, they don't glue. They don't satisfy the gluing condition, so they don't coincide on the double overlaps. So that doesn't work. A famous example where this happens is when we look at the Hopf vibration, 3 sphere over the 2 sphere. The Hopf vibration is an S1 bundle. So here it's a T1 principal bundle. And then they considered the simplest additional data that is available. So the metric on the 3 sphere is just the standard metric. And the B field is just 0. That's definitely the simplest situation one can look at. But already in this simple situation, it is not true that the dual G and B, so note that B hat is not 0 because the Buscher rules mix G and B hat gets components from the standard metric. They do not glue to metric and B field on the 3 sphere. But then by staring at the formulas, one can sort of see easily that they glue on another space, namely on the trivial torus bundle over the 2 sphere. Okay, so trivial 1 torus bundle over the 2 sphere. And the formulas we get for dual metric and B field are just so that a globally defined metric on this other space is obtained. And that's exactly the topology change that's mentioned here. So the target space changes its topology from 3 sphere to this product space. And that was very interesting for the topologists. Right. So before continuing this strand of discussion, I wanted to recall or outline how we treat B fields in general topology. Namely, it is so that the two-form description of B fields gives only like the local aspects of B fields, while it is sort of right now sort of more or less well understood that the actual B fields are described by bundle gerbes with connection. So as Raphael said at the beginning, so Christoph Glawetzky made like important contribution to this point of view, in particular when about in the situation of WZW models, so sigma models on compact Lie groups, where the topology is really important of the target space. So let me briefly recall what a bundle gerbe is and how it's obtained. So when we said here that B fields, so two forms, only give the local description of B fields. So we think about a general B field as consisting of locally defined two forms, so B alpha on open sets of the target space. And then on the intersections between open sets, we do not require that the two forms coincide, but we allow a gauge transformation. And the gauge transformation of two forms means that there is a one form. So on a double overlap, there is a condition.
Konrad, just a very stupid remark, but that may lead to confusion because you're writing X, and it seems that you're putting the gerbe on the base of this toroidal vibration. Are you doing
Yeah,
this
I'm sorry for that. Exactly. So here I just wanted to explain like, the general situation.
I know, but I want to. Yeah,
we could just put M here exactly to not confuse people. Right, exactly. So whatever the target space is, we choose an open cover and then represent a general B field as being glued together from two forms. And on the double overlaps, we do not impose equality. So that would mean that we have just a globally defined two form, but instead we allow that there is a gauge transformation obtained by including the differential of a one form on the double overlaps. So we have here one forms, A alpha beta, one forms on the overlaps. So that's the idea. And then it goes on similarly. So now going on triple overlaps, we have these one forms on the intersections, and there is a similar rule if I pass from an open set alpha to an open set gamma by applying the gauge transformation by A alpha gamma, then that should be the same as like doing twice the gauge transformation from alpha beta to beta gamma. But still there is yet another construction, because now I have like two one-form potentials, and I do not require that they are equal, but rather that there is an actual gauge transformation parameterized by like a function, a U1 valued function that now lives on the triple intersections. So C alpha beta gamma function on triple intersections. And that function in turn now satisfies the Schick co-cycle condition. And that's it. So by just imposing that the B field is glued together using these gauge transformations, and they are in turn glued together by gauge transformations, then this gives the right notion of a bundle gerbe with connection. So that's what we have. So, well, or rather more carefully said, so these C's, A's, and B's are like the local data for a bundle gerbe with connection, and in the same way that you can describe a principal bundle with connection by transition functions and local connection one forms, bundle gerbes with connection can be described by this local data. There is also an invariant coordinate-free way to say what a bundle gerbe is, but we don't need that today. And so once we describe B fields using these bundle gerbes, we can like single out these three interesting properties that a bundle gerbe has. First of all, there is curvature. So the curvature, if the bundle gerbe is given by this local data, then the curvature is obtained by taking the derivative of B. And you see from this equation that the derivative of B is in fact globally defined. It glues together on the double intersections. So the curvature is always a globally defined 3-form on the manifold M, and that's the H flux of the B field. So although we have generalized the notion of B field, it still has a well-defined 3-form H flux, and that is actually closed. Okay. So we have extracted this H flux at the top level of structure, but we can also look at the lowest level of structure, where we have this function C, and it just plainly satisfies the Schick co-cycle condition, and hence it represents a class in the degree 2 Schick cohomology of the manifold with values in the sheaf of U1 valued functions. And that Schick cohomology group, it's well known using the exponential sequence on the coefficients to be canonically isomorphic to degree 3 cohomology. So these bundle gerbes also have topological information, namely degree 3 cohomology classes, because degree 3 cohomology classes appeared before in operator theory and Dix-Médois-D classification of continuous trace algebras. This class is also called the Dix-Médois-D class, although a priori it has nothing to do with operator algebras here. And the third property of these bundle gerbes, I don't want to get into the details here, is that they have this so-called surface holonomy, which basically means that one can still make a well-defined sense of this coupling term phi star B in the action function of a string, even if now B is only locally defined, so that these gerbes can still be used to define like the action functional of the classical string, bosonic string. So from now, we will always consider triples of an arbitrary torus bundle, an arbitrary Riemannian metric on M, and an arbitrary bundle gerbe with connection on M, which you can safely think about as given by local data like this. Any more questions about this? So here there are two things we need to know about these bundle gerbes. The first thing is that they actually form a category. So what does it mean? It means that there is a well-defined notion of morphisms between bundle gerbes. That's probably not too surprising. So if we imagine that we have two bundle gerbes given by like these triples of local data B, A, and C, and we have another bundle gerbe given by primed quantities, C, alpha, beta, gamma, C prime, then a notion of morphism between those will consist of something like gauge potentials, call them A tilde, but now on the open sets itself, such that like making up the difference between the B's. Okay. And then on the double intersections, now it gets a bit complicated. We can compare the one forms of one gerbe with the one forms of the other gerbe, and then get a difference term in relation to, with these new gauge potentials we have on the open sets. So we take a check differential of those and evaluate this as the alpha beta. So this, so tilde. So this means just A tilde beta minus A tilde alpha. And then for good measure, we also allow here a gauge transformation, so d-log of a function G alpha beta on double intersections. And then there is finally, should have moved this? Let's see if it goes. Oh, no. So that there is also a relation between these C's, namely just a check relation like this. Okay. Oops. All right, so there is a natural notion of morphisms, and one can sort of rather easily say what they are. And I should explain how the old B fields embed into this picture. So if we have this category of bundle gerbes, which we denote like this is a category, and the old B fields were just the two forms, okay? And so there is like nice embedding. If I have a two form, a globally defined two form, then I just insert it into this bundle gerbe picture by taking B 0, 0. So this works because when B is globally defined, then the A's can be taken zeros, and when the A's are zeros, then the C's can also be zero. But there is this well-defined embedding, which is just saying that like the old B fields,
well, C's cannot be zero; they can be one, right? That's
oh,
it's
yeah,
a zero in the other notation.
Okay. I write one exactly. You're right, because it's U1 valued. Yeah. So the old B fields are like nicely embedded into this more general point of view. And another map one has is the projection to the curvature. So we can go to the three forms by going to the curvature. So yeah, so let me, so this thing would just go to dB. So that means if a bundle gerbe comes from globally defined two form, the curvature is just dB, so it's exact. But in general, there are bundle gerbes that are not, that whose curvature is not exact. Okay. I should also give this a, oops, that was not, give this a name. So this bundle gerbe here, coming from a globally defined two two form will be called IB. So this is like a topologically trivial bundle for bundle gerbe with only connection data B.
Excuse me,
Yeah.
one question. So if we would consider instead just two forms on a given atlas of charts, whose differential, the RAM differentials coincide on the intersection, then we would get bundled gerbes without connection. Or am I wrong?
Okay, so we would consider locally defined two forms such that dB alpha is equal to dB beta. Then what we get is, or what we could look at is the following. If we could look at the difference. So that's a two form on
I see.
the double intersections. And that tells us that it's closed. And then by making the open set small enough, then the closed things also become exact. And that means that one can sort of choose.
Yeah. So you can
something.
reduce yourself to the previous situation.
Exactly, yeah. So it
But
turns
this
out
definition seems to be simpler than because it doesn't refer to any A's and C's.
that's true. However, the continuation of the structure to A's and C's will not be unique. And the different choices will make up different B fields. And when you look
Okay, so because I don't know the future, so
yeah, so this data of the A's and B's, this is really belongs to the data of the B field. And even if we have a situation where it exists, it's important to fix it because, for example, the string coupling term that we make up here doesn't, this is just like, that's not the full truth. I mean, the A's and C's also enter the full definition of the surface holonomy term, and changing them will lead to another coupling in the action functional. So it's important that the whole structure is given and fixed as background data.
okay, thank you.
All right.
And I would like to make sure this whole thing, this whole category is associated to one particular bundle. Yeah. So this is the for if I change M, I obtain a different category.
Yes, it's exactly. It's like a sheaf of categories. To every manifold, it assigns a category of bundle gerbes over it.
Thank you.
Okay. Right. So the second important thing I wanted to mention is what happens. I mean, this is something about the category. What happens when I ask what are the morphisms between two bundle gerbes that are both of this trivial kind, so come from old B fields, which are globally defined two forms. And there is a theorem saying that, well, these homomorphisms correspond to principal U1 bundles with connections over M, and the curvature of these bundles picks up the difference between these two B fields. So let me try to sketch the proof of that statement. So before we have like defined here or looked at here what the morphisms are in general. So we have to reduce these equations to the situations that the A alpha beta and the A prime alpha beta and the C's are all 0 or 1, and then see what these equations become. And they become here the first equation. So there is a B prime, which is now globally defined, a B and a D A tilde alpha. And the second equation, so we have 0 here and 0 here. And this means that A beta is A alpha minus D log the G alpha beta. And the last equation is just saying C and C prime are 0. So it's just saying that the G satisfies the Schick co-cycle condition. And what we have here is exactly the local data of a principal U1 bundle given by the transition functions G and connection A. such that the curvature of the connection, which is locally dA, oh, I forgot the tildes, sorry, which is dA, is equal to the difference of the b's. So that's like a sketchy proof of this lemma. Okay, that's going to be important in the second part of the talk.
I'm a bit disturbed by these alphas and alpha betas. So you probably mean in the first equation, for example, restricted to U alpha or what?
Here? Yeah, that's an equation on U alpha, yes.
Wait a second.
Better?
Yes.
But this is just a classical data for principal U1 bundle with connection, right? So this is a formula that you write down for the transformation of the gauge potential under the transition function. Okay. So I will now jump back to the Buscher rules first. And so now we are kind of equipped to generalize the Buscher rules. We now know what the generalized B fields are. So the metrics we don't have to generalize. We know what metrics are on manifolds of arbitrary topology. So there is no generalization to do there. But now we know exactly what we have. We have principal bundles, torus bundles, we have metrics, and we have bundle gerbes. And now we go on to generalize the Buscher rules into that arbitrary topology setting. And as you noticed before already, here is some Kaluza-Klein theory in the background lurking. And so this is just to recall what this aspect of Kaluza-Klein theory says. So it's related to the situation that we have a metric on the total space of a principal bundle. So it lives on the total space. And then one can just break it up into a smaller structure, namely a connection on the bundle, a metric on the base, and a family of metrics in the fibers. So you can imagine that the connection, you know that the connection splits the tangent spaces of the total space of a bundle in horizontal and vertical components. The horizontal components are isomorphic to the tangent space of the base. So that's why we get the metric in B. And the vertical components are just the Lie algebra of the gauge group. And this gives this family of metrics in the fiber. So in general, like this fiber metric can change. It's parameterized by points in the base manifold.
But the connection, so to say, is the mixed term of the metric, right? But then it would be not a connection, a principal bundle, or not a principal connection, just any connection, right?
Here it is a principal connection, principal bundle connection. That's exactly
but
what
then you require the metric to be invariant or something, or what? Under the U1.
Oh yeah. Yeah, sorry, I guess you are right. We need to require the metric to be invariant. Yeah, sorry, I forgot just to write
But
this.
then otherwise this would be just any connection, but not a principal one.
Yeah, okay, you are totally right. I forget to put this here. An invariant metric on the total space of the principal bundle. Exactly. Thanks.
But a priori, it could be that there is no connection, yeah?
It could be that there is no connection. I don't know what you mean. I mean, this is a theorem that there is one-to-one correspondence between these things. So
But the invariance is an assumption.
there is now, that belongs to this first phrase, yes.
He's assuming that the fibers are compact. That ensures that the corresponding Eresman connection is complete. So you are assuming compact fibers.
Not that I know. I mean, this theorem is really simple. You just translate data. I don't see why.
It actually doesn't work even in the non-invariant case. You need you are constructing in general you are constructing an Eresman connection, and you need it to be complete in the sense that it has a complete parallel transport. Otherwise, it doesn't work. So that's ensured if the fibers are compact, for example. It's well known in Kaluza-Klein theory, by the way.
Okay, first, I don't think so. I mean, this is really simple. I mean,
no, it is really true. I insist, and you can check. I can give you references if you want. There
As
is
I
an,
said, I mean, the connection is supposed to split the tension space into horizontal and vertical part. I think every connection does that. And once that's done, the metric just
you
splits
won't,
this.
you won't have an equivalence between these data unless there's some extra condition. It's subtle, but it's true.
No, but how do you construct principal connection from a connection? This is not possible, probably, in all cases.
Yeah, it's the same issue. So it will be possible modulo this completeness assumption. There's a very general and precise discussion of these issues in a paper of mine with Kahle, Schick, but of course that's not the point of the paper because in some sense it was well known before.
So you say any principal connections automatically complete or what?
No, if you have completeness.
He didn't write complete, right? He didn't write complete in A. He didn't say connections.
In general, you get an Ehresmann connection. If that connection is complete, then you can associate your fibration to a principal bundle in a very precise sense. So you have to read a paper of mine with Kahle, Schick from like 5 years ago. We explained this very generally. But I mean,
again,
that's a general case and what he assumed. But anyway, I mean, this is a divagation. It's not important, I think, for the purpose of his talk. So if you want, I can send you the reference.
Right.
No, but if you have invariant metric, then of course you take the vector space orthogonal to the fibers,
right?
And it is preserved by the group action.
Yeah, but I think there's still an issue of compactness of the fibers.
No, but this is an
No, I think invariance is
complete
fundamental here. Invariance of the metric.
Yeah, but if you have a non-compactly group under which it's invariant, I think there's a problem.
So my intention was to present this as a well-known theorem, and except for that I forgot to put invariant, I think it's true. As
I would agree with the invariance assumption.
Yeah, sure. The invariance is like not. I just forgot it to write it. That's not the point. No, it's just invariance is okay. Okay, so I would like to use this Kaluza-Klein theory to split up the matrix G that we have on this toroidal backgrounds into the data that is predicted by this Kaluza-Klein theorem. So we have the metric G on M, and now it splits up into a connection, which I call omega. So omega is a one form on M with values in the Lie algebra of the structure group. The structure group was a torus, and I deliberately take the Lie algebra to just be Rn of the torus. And then we have a metric on the base, which I denote by just G prime. So it's on X. M was this principal bundle. And we have this family of metrics in the fibers, so that I denote by H, and the family, so that depends on a point in the base. And so now let's look at the lemma that I write here at the bottom. So we want to give a coordinate-free expression of the Buscher rules. And here the claim is that the Buscher rules, exactly the ones that I presented on the first slide, are equivalent to these three coordinate-free equations. The first equation, let me just put some additional things. So here we assume that we have now, we're talking about the Buscher rules. So we are going back to this topologically trivial situation, because otherwise we don't know what the Buscher rules are. So we have
excuse me, one remark about the metrics. Of course, this family of metrics should consist of invariant metrics.
That is an interesting discussion that I also had with people, but in the end, yes, I think you're right. Sorry, yes, I also forgot that to put, you're completely right. Family of invariant so invariant here means of
Yeah,
course.
this is necessary condition, of
Yeah,
course.
it means of course that it's at invariant in the fibers. Yeah, sorry for putting the theorem wrong. I forgot 2 times invariance, yes. Better?
Yes, of course.
All right.
Konrad, just bear in mind that you can at some point break the flow and send us.
I break it in 1 minute, okay?
Okay, sure.
Okay, so we assume that we are in the situation of the Buscher rules. So we have 2 pairs, GB and G hat, B hat, both on this trivial kind of string background. And now we break up both metrics into components. So we get here another connection omega hat, another metric on the base G hat prime, and another family of fiber metrics H hat X. And I claim that the Buscher rules are equivalent to a set of 3 equations which concern these 3 things. And these 3 equations have the nice feature that they are coordinate independent. They are just global equations. So the first 2 equations are easy. They just say that the 2 metrics on X that we get from the left and from the right side are equal, okay? The second equation says that the fiber metrics we get from the left and the right-hand side are not equal, but are inverse to each other, right? So we are talking about metrics. So what does it mean? A metric in the fiber means a positive definite matrix, n by n matrix, because the fibers are tori. And so we can just invert this, the inverse matrix. That sounds a bit crazy. In the original work of Buscher, and also in like many treatments of T-duality, you find the claim that T-duality inverts the radius of the string. And that's exactly that point, right? That's a fiber-wise metric is the radius of the toroidal compactification. And this second equation here says that the metric is inverted. So also in 1 dimension, it means just the scalar, the radius is inverted. Okay, the interesting part is this third equation here. So, and for that, I just wanted to make 1 comment where it is defined and where it comes from. So this is an equation that lives on an interesting space, namely where the torus dimension is doubled. Okay, so there is 2 times torus coordinates. And this space has projections to the left and the right-hand side. So I'm writing it like this because that's going to be an important picture that we're going to have. So this is also called the correspondence space, and it has projections to the left space and the right space, which are equal here, but later they won't be equal anymore. Namely, the projections that the Euclidean space coordinate is just preserved, and the 2 n torus coordinates are split into n left ones and n right ones. Okay. And now I only have to explain what this little 2 form here is. And this 2 form, okay, so these are all 2 forms. It's an equation of 2 forms on that space. And this 2 form is obtained from these connections we get from the Kaluza-Klein theory, namely just by pulling them back. So this map will be called P and this P hat. So we pull everything back to this correspondence space from the sides where they are defined. And then here we just take the wedge product. That makes sense, right? These omegas are 1 forms with values in Rn. So we can take the wedge product and on the values just use the standard scalar product of Rn. And then we get a well-defined real valued 2 form on this correspondence space. So the B's also pull back to this correspondence space. And the omega that appears here that's just another form, namely the canonical form on the torus that's given by a formula like this, the 2 torus. Oops. Read this. Wait.
What is H?
Where is H? Oh, H. Wait, sorry.
Fiber
H
metric.
is the fiber metric.
Ah, okay.
Okay, so that's the 2 form omega. So it's a 2 form on the 2 torus. And it's in fact a very interesting 2 form, namely the curvature of a bundle on the 2 torus or the 2n torus, namely the Poincaré bundle. It's a particular bundle on T2n. It has a connection, and the curvature of that connection is this 2 form. All right, so that would be a point to stop and make a break.
Okay, so since it's 3, I propose that we meet 3, yeah, 10 minutes break.
Okay.
Mikrofon do wyłączenia.
Konrad? Hallo?
Ja. Hallo.
Ja. So. Wir fahren weiter.
Can we continue?
Yes, please do.
Okay. So since there was some discussion, so let me try to point out the proof of this theorem here, of this lemma, namely that the Buscher rules are really correspond to these 3 simple equations. And in order to do so, we have to go through this Kaluza-Klein theory and see what, like say on the left-hand side, where we have this metric G on Rs times Tn, what we get through Kaluza-Klein theory from that exactly. So recall that for the Buscher rules, we split it up, G, into these diagonal and off-diagonal components. And now we want to express them through the Kaluza-Klein data of G. So recall that from G, we get the connection omega, the metric G prime on the base, which is Rs, and the fiber metric H. And the first point would be to have a nice coordinate way of talking about these things. So the metric G prime on Rs and the metric H on the fibers, that's sort of fine. But the connection, how do we talk about connections in coordinates? We consider their connection 1 forms. So we will write the connection omega at a point, say, x, a, where x is here and a is here, to be a connection 1 form, a, just depending on the base, and some d log a. So that's the standard way of going from connection 1 forms to local connection 1 forms a on the base. And once having done this, this Kaluza-Klein theorem tells us what these metric components are. Obviously, let's start here at the bottom. So this was meant to be the component of the metric in the fibers. So this is just the H, the fiber metric. Okay. Then the metric here was the horizontal part of, or is supposed to be the horizontal part of the metric, exactly. And that's given by this metric G prime on the base, plus a contribution that comes from this connection 1 form in order to say what the horizontal tangent spaces are. So there is a contribution looking like this. And then the off-diagonal parts are a mixture of this fiber metric and the connection, like this. So these equations come from this Kaluza-Klein theorem, translating the data of the metric on the total space of this principal bundle to these three components. Okay. So now the Buscher rules were concerned with this side of the story. Now we can substitute these equations in the Buscher rules, both for the metric G from the left-hand side and for the metric G hat on the right-hand side. Okay. So let me see what this gets. So substitution. So I don't want to do the full discussion here because it takes like hours because the Buscher rules are complicated. But just to outline roughly what happens is that we get equations, for example, for the dual B off-diagonal parts. They will just be the metric components, and the base part of B, there is a rule that looks like this. So you see the equations are not getting easier, they just change a bit the data. So now this is an equation for the B's and the A's. And
apparently there are too many hats in the last formula.
Too many hats in the last formula. Yeah, absolutely. Better?
Yep.
Yes, exactly. I mean, the Buscher rules separate clearly all the hat things on the left and all the things without hat on the right. So that's still preserved here. So equations like this drop out from that. And now the next task is to transfer this equation that I claimed is equivalent into coordinates and then see that in coordinates we get the same structure. So for example, we could like see what this formula here gives us in the ij component. So or let's rather first wait, that's too much for one. Let's just look at this kappa thing. What does this give in components? So let's look at the ij component of this kappa. Okay, and for that we go back to the definition. The definition is this here, and so we have to evaluate the wedge product of these omegas. Omega is given by this thing, so if we do that, we get like alternating products of the A's. So analyzing this in detail yields a formula like this. So now the A's and the A hats are really mixed. Okay. Like this. And now we can start.
Exact part, D log A.
D log A. So this is, yeah. So here, this is just the way of how the connection one form on the total space goes to a local connection form on the base. So maybe it's not the best way of writing that. It's just saying that the form on the total space has a part that sits on the base and sees this one form there, and the vertical part of the connection one form is just given by d log of the coordinate. So I could also write, maybe that's better, the Maurer-Cartan form on the fiber, right? A connection, if I restrict it to the vertical tangent part, it looks like the Maurer-Cartan form. And if I restrict it to the horizontal part, then we see one form on the base.
So it seems this is just a change of coefficients when you choose another complementary vector space, yeah? So this is, if you have vertical subbundles, so then you choose vertical horizontal vector space. So this is the change from the vertical for the orthogonal complement to any other complement.
That's how this Kaluza-Klein theory works, right? If you have this metric on the total space of the bundle, like the vertical tangent space is always there. It's just that's vertical is clear. And if you have the metric, you take the orthogonal complement of the vertical tangent space, and this defines your horizontal tangent spaces. And by that, you get the connection then. So that's like included here into this procedure.
So this is linear algebra from the first year. Yeah.
Absolutely.
But by the way, in this first year thinking, so I still don't get why wedge omega hat doesn't contain any details, any Maroccaton terms. If I just plug it in, I get them. So why are they not here now?
So here, because we're looking at the IJ component here, right? The theta's are in the fiber component.
Okay, I see. I get it.
Okay,
yeah, thank you.
We get them when we look at the other components. But we have now splitted the space. This double space here now has like three components: the RS, the first T, and the second part. So we have like 6 components now to analyze because it's anti-symmetric in 3 by 3. So 6 components. So I don't want to provide all of them. That I have to go.
I see. Understand. So the IJ is this RS, right?
Yes, exactly. That's the RS coordinates. I just wanted to give you like a brief idea of how this works. So basically, you write down everything in coordinate, substitute these Kaluza-Klein things, and then observe that that these 3 equations, split it up in components, are exactly these Buscher rules equations. That's the point. Mm-hmm. Okay, maybe I stop this now because. So let's stop the proof. As you said, it's a bit linear. It's like linear algebra a bit. It's sort of funny, but one can do it. So, all right. So the main point of
can you still say what I mean? For me, it was too fast. Now, if you just stop. So
yeah, I haven't completed it yet. Because there's many things to do, right? So
you compare what with what?
Yeah, look at this equation that I claim is important, and now analyze, for example, the IJ part, so the base part of it. Then this form here gives this expression. The omega is a form that lives purely in the fibers, so in the double torus. So this has no IJ components. So here the IJ component is 0. Okay. And this will give us the Bij, and this will give us the B hat Ij. So the Ij component of this equation gives an equation saying Bij hat equals Bi. Yeah, so it gives, okay, Bij. Then the omega is 0, and the contribution of this kappa is this here, okay? Okay, good. And so now I claim that this Buscher rule equation corresponds to this equation that comes from the right-hand side, namely exactly under the, okay, we need the other, so there is another equation saying that, so the converse equation also holds here, Bij equals A hat Ij, and using this here gives this equation.
Thank you.
So that's like the proof that in the Ij component, the thing corresponds to each other, and then one has to go through all these 6 components and just compare it. All right. Yeah, sorry for not giving all the details here, but yeah. So let's move on. So yeah. So one important thing that I want to conclude from this story here is the first thing is that it makes sense to look at this correspondence space, which is like the fiber product of the target space of the left and the target space of the right. So that's one one experience we make, that that it makes sense to look at this correspondence space, this doubled space. And the other thing is that we see that this form, this two form here appears. We could also make a quick sanity check, take this third equation and look what D of that is. That's also quite insightful. So if I do this, so the D of the B field is always the H flux. So I get something like pullback of the H flux from the left, pullback of the dual H flux. And then omega, I said it's the curvature of the Poincare bundle. So as a curvature of a bundle, so D of that is 0. And the differential of this form, the kappa is, okay, is some two forms. So it's just D of that. It doesn't have any particular meaning, but it is saying that the H fluxes on this correspondence space are related by this equality. Okay, now we're trying to generalize this to the situation that the target spaces on left and right now have arbitrary topology and not this product topology anymore. Okay, so that's shown here. Okay, and I see because I moved this around, got a bit destroyed. That's not so nice. I'm not sure. I don't know what happened. So here was supposed to be the what's going on now? Okay, I don't understand that. Just okay. Anyway, so what I want to say is that now if we have general target spaces, so which are torus bundles on both sides. So we learned from this analysis of the Buscher rules that we should look at this correspondence space, and the general form of this correspondence space is that we take the fiber product of the two torus bundles, right? So this means the base coordinates are not doubled because it's a fiber product, but the fiber coordinates come from both sides. And that's an important picture that you might have seen also in the T-duality context. We are drawing these correspondence diagrams. So now let's try to generalize these coordinate-free equations to this general situation. So recall that we assume now that on the left we have a triple MGG. So M is a torus bundle, G is a metric on M, G is a bundle gerbes connection on M, and on the right-hand side we also have the dual data. Okay. Then we feed this metric in the Kaluza-Klein mechanism. We can do this also here in this non-trivial situation and get triples omega G prime, the base metric, and the fiber metric. It's the same here. Omega hat, G prime hat, G hat. Okay. And then the first two equations of these coordinate-free Buscher rules equations, they just make sense as before. So let's already denote them here where I wanted to put the final general Buscher rules. So the first equation will be that the base metrics coincide. That's just as before. And the second equation will be that these fiber metrics are inverse to each other. Okay, I have to write it here. So H is equal to H hat to the -1. That was already the first two equations we just had. Just the third equation. So remember, I'm talking about this equation here in the middle, this equation. So now this equation does not have an immediate generalization because we don't have these B fields anymore. Now we have replaced the two forms by general bundle gerbes. And so we cannot write an equation of two forms now because we don't have any two forms, basically. A little motivation is this consequence that we want to keep because the H flux, recall that the H flux was the curvature of the bundle gerbe and it's still a well-defined three form. So we can talk about three forms in this bundle gerbe context. and we want this equation to be satisfied. So this gives us an idea what we have to look for. It says pull back the H fluxes to this correspondence space, and then they are equal in cohomology because they just differ by this exact term. So we take this as a motivation of what to do on this correspondence space. Namely, we will pull back the two bundle gerbes to correspondence space and then require that they are isomorphic. So we will put something like this. An isomorphism. So now it's important that bundle gerbes form a category. So this gives me the possibility to say, choose an isomorphism of these bundle gerbes. And now it's a statement that the curvature of isomorphic bundle gerbes is equal. So requiring or putting an isomorphism like this would yield the equation for the H fluxes P star H equals to P hat star H hat. But that's not the equation we wanted. We wanted this differential of kappa there. And that we include simply by taking a tensor product with the trivial gerb with this two form kappa. Kappa was this two form. For every two form, we obtain a topologically trivial bundle gerb that we denoted by I. This was this B01 bundle gerb. And now we require an isomorphism here. So let's call this D, for example. So we want that there is an isomorphism. All right. So that's
Konrad,
yeah.
Sorry, maybe it would help if you in this Valentino picture that you're using throughout showed what the monoidal structure is, so what the tensor product is, because this hasn't appeared yet. I mean, it's
the tensor
particularly
products,
simple in this picture, right?
yeah. My plan was to sweep this under the carpet, yes, because it's not going to appear really explicitly. So let me just say it. If you talk about this local data of bundle gerbes consisting of these two forms B, the one forms A, alpha, beta, and this Schick co-cycles C, alpha, beta, gamma, one can just add all the data. So add the two forms, add the one forms, and multiply these Schick 3 co-cycles, and that makes up the tensor product of bundle gerbes. So that has a very simple definition.
Again, what do? You add two forms or what? What again?
I just explained on Raphael's request what this tensor product here means.
Yeah, understood. But can you just repeat what you said?
Okay, so sure. So let me just write it here. So this is a bundle gerb. Say it has some data consisting of B alphas, or maybe I should put hats now, B alpha beta hats, and C alpha beta gamma hat. And then here comes the tensor product with this trivial thing, which just has in the first component this kappa, and then 0 and then 1. And in order to define what this tensor product is, we just add this data. So add this data. So the new bundle gerb, the tensor product bundle gerb, has the sum here, and then the sum here, which says do nothing, and then the product here, which also says do nothing. So on this level of local data, the tensor product is just add component wise.
Thank you.
Yeah. Okay. All right. So as I said, as soon as we require that there is this isomorphism, we have this equality for H fluxes that we also see from the local picture. But still, this is just a consequence of the Buscher rules. It's not equivalent. So we need to implement this equation in some way, also involving this curvature omega of the Poincare bundle. And that's not done yet. And therefore, a fairly sort of complicated condition is formulated on this isomorphism D. And let me explain that. Namely, it says that we're doing something that we did at the very beginning, namely we trivialize locally and then fix a local rule. So how does this look like? So I want to trivialize this diagram locally. So the condition 3 is the following. So there exists local trivialization of the bundles. So how would they look like? They would look like this. Phi's go from open subset. So I'm just working on one patch. I don't have to analyze transition functions. I'm just looking on an open set U of X and find a diffeomorphism to the restriction of N to U and so on. So I trivialize locally the bundles. Okay. So on the same patch, I want a local trivialization of the dual bundle. Okay, fine. And now I have trivialized the bundles. And now I want to trivialize the bundle gerbes that live over these bundles. So I want to trivialize, so I want to pull back the gerb G, which lives here over M, along this trivialization. Then I'm here on this product space. And I require that this bundle gerb is of trivial form, then I of B, for some B living on this product space. Okay, and the same on the dual side. So here we require that this bundle gerb is also trivial. So this is a local triviality condition that we are imposing on this structure consisting of torus bundles and bundle gerbs over them. And now something funny happens. Let me try to make this bigger. Namely, we can do the following. So we want to transfer this trivializations correspondence space. And first of all, the phi's combine to a map from the local version of correspondence space, just small open set, and then double torus to the actual correspondence space by just using like phi on the first n torus coordinates and phi hat on the second n torus coordinates, okay? And then we will pull back this isomorphism D along this map phi. So let me write this. So the pullback of D. So pullback now just works like intuitively. So if I pull back this gerb morphism, then I get pullbacks on both sides. So I get
Konrad, if I may interrupt, because so this looks a little non-obvious that if on pulling back by phi, say the gerb from M to a space which has non-trivial topology, you're getting a trivial gerb. So am I to read it as the statement that one cannot really proceed with considerations in more general cases where the pullback is non-trivial, or how am I to read it?
Yeah,
Because
that's exactly
it doesn't
the point.
follow. It's really a constraint. Yeah.
Yes, I'm imposing conditions here, and if it's impossible to find, I mean, I can always make U like arbitrarily small. Okay, so
sure, but P and state, right?
To make it small on the base. But you're right, the fiber stays always the torus. So it might happen that the bundle gerb just does not become trivializable, whatever I choose as U. And it happens precisely if like the bundle gerb is concentrated in complete fiber direction. And in that case, the thing cannot be T-dual in that sense to anything else. Yeah, it's excluded.
Is there some conditional small phi and small phi hat to combine into capital Phi?
No, we choose the phi's arbitrary on both sides, and then whatever they are, we combine them to this phi.
Because you have only one U, and there are two U's then in phi and phi hat.
So phi applied to a point U, and then a point in the double torus, let's say like this, is just phi of UA. So I use the same U. Because
when needs to check that this lives in the fiber product now, right?
Exactly, yes. I have to land in the fiber product, so I have to use the same U.
So maybe, but does it not impose a condition on phi and phi hat, this condition?
No, I mean, they are, yeah, sorry, I didn't write it. Phi, they are local trivializations. So they preserve the projection to the base.
Yeah, right.
That's what I understood, yes.
Yeah, okay.
Yeah.
And then more down to earth, can you explain the last line? Because Rafa jumped ahead. He understands this already, but I don't.
The last line I wrote?
Yeah.
So sure. It's also not ready yet. So recall that we sort of agreed, or I persuaded you that we have to consider such isomorphism on correspondence space. You pull back the gerb from here, pull it back from here, then require that they are isomorphic, and there is this intriguous part here that takes care for this Kaluza-Klein forms that has to be included, because we already saw in the local situation that it's there, this term. So we have this isomorphism. And now the plan is to look at this isomorphism under the local trivializations that I chose here below. Okay. And let me complete writing it. So this is our D, that's the isomorphism. We pull it back. I was not ready yet. So here, oops, because here is now the pullback of this Kaluza-Klein term. So I, kappa, omega hat, and so on. And now I would like to use several things. For example, on this side, we can like exchange the two pullback maps in the following way. So first pulling back the gerb to correspondence space, and then along this local trivialization is the same as first pulling it back along the local trivialization and then to the correspondence space. So there is an equivalent. So this is like canonically equivalent to this thing here on the left. And then I am in position to use my trivialization here. So we get something like I P star B. Okay. The sort of the pullback commutes with forming the trivial bundle gerb. And this is nice because the P star B is exactly what we have here in this equation that our aim is to generalize. Okay. Good. So let's work on this in the other direction too. So here we do the same thing. We commute, get the phi hat, g hat. Okay. And here's some tensor product. Here nothing happens. Here I just pull this down in the index. Doesn't matter. Don't worry about this. And now use the other trivialization here, making the other gerb trivial. So this is equivalent to, or isomorphic to, again, a trivial gerb, but now with B hat plus this Kaluza-Klein term. Okay. And so by running through this composition, the D was like the only data I imposed for the T-duality. The other things are canonical equivalences. This gives me an isomorphism between trivial bundle gerbs with connection. Okay, and now let's remember that I prepared in the first part of the talk the statement that the isomorphisms, the morphisms between trivial bundle gerbs with connections are precisely the principal U1 bundles with connection whose curvature is the difference between these two forms. And now we are in position to impose the third condition. So far it was just like they exist and so on, such that this isomorphism is this Poincaré bundle with its connection. So there is a specific U1 bundle with connection over the double torus space, and we impose the condition that this bundle corresponds to this isomorphism between bundle gerbs.
Why is it called Poincaré bundle?
Yeah, that's a good question. Yeah, I don't know. I think it's because under circumstances, the curvature, this omega curve, that looks like a symplectic form, maybe. Maybe it has something to do with Poincaré recurrence or something, but I'm not sure. I don't know. It's called Poincaré bundle in this, I think, maybe Mathai or Hori called it the Poincaré bundle. There is this Hori formula for transformation of fields in T-duality, and it involves this Poincaré bundle. Somebody called it Poincaré
It's a
bundle.
bundle over X with fiber to two torus. I mean, two N torus. Is it correct?
No, it's a bundle over the two torus, T to N.
The other way around.
It has nothing to do with X. It is just fiber. It's a fiber information, a fiber-wise information.
Yeah, okay, sure.
Yeah. And so this is saying that the curvature.
It's a U1 bundle, or what kind of bundle is it?
Yes, a U1 bundle, yes. A U1 principal U1 bundle with connection. And the curvature of this bundle, that's this form omega, that by construction of this gerbe theory is now the difference of these two forms from both sides. So it is the difference we had plus phi star kappa omega hat minus p star b. And that is exactly this equation that we wanted to generalize. Right, you put this to the other side, and then it becomes this equation here. There is a minus wrong. What's happening? Yeah, okay. Never mind. Maybe there is a minus. That's not the point here. So the point is that we have found like rules that make sense for string backgrounds, toroidal string backgrounds with arbitrary topology. And these rules have been motivated by the local way how it works. And that local way was given by the Buscher rules. So let me pass to this picture. Okay. Somehow this program scrambling up things. What's happening here? It's not very nice. Okay. So what we just did on the last slide was to give a definition of what I call, not sure if the name is good, geometric T-duality. So it means T-duality in fully general topology with everything equipped with full structure, Riemannian metrics and bundle gerbes with connections, right? So the bundle gerbes with connections, they include the differential geometric aspects of B fields and the topological aspects of B fields. And so this diagram is more or less a theorem that I proved in my paper. That's called exactly how the talk is called, Buscher rules and general topology. Namely, so here just confirming on that side that if we look locally, so trivialize everything over an open subset, then by what I explained earlier, we get this gerbe morphism that corresponds to the Poincaré bundle. And then by translating that, we get exactly this equation in this lemma, which by the lemma corresponds to the Buscher rules. So one can make all this very precise. And so this geometric T-duality picture that I just drew implies locally these Buscher rules. And here I'm indicating that it implies several versions of T-duality that have appeared in the literature. This is the mathematical literature, of course. So for example, this T-duality with H fluxes, which was probably the first mathematical rigorous description of T-duality by Bouwknegt, Evslin, and Mathai. So here, this picture of T-duality with H flux disregards the metrics, so it's only about the torus bundles. The metrics are forgotten, and the bundle gerbes are replaced by only their curvature. Only the curvature information is used, and then they have a notion of T-duality in that setting, which is implied here because our setting is more general And if I have bundle gerbes, I can anytime pass to their H fluxes, to the curvatures, and get into this picture. So similarly, there was a picture that was called differential T-duality. In that picture, the metrics were also forgotten, but not completely. The Kaluza-Klein connection omega that belonged to the metrics, that was preserved here. And the bundle gerbes too. So this is pretty close to our picture, this differential T-duality, though the setting and description is slightly different. So this correspondence arrow is like a longer translation of different ways to represent things. And then we can also pass to this thing called topological T-duality. So mathematically, this is like the most famous and most studied thing, where all the differential geometric information is forgotten. So the metric is forgotten, and the connections on the bundle gerbes are also forgotten. Just the topological information of the bundle gerbe, which is basically the Dix-Mildois-D class, is preserved. And there have been like very nice results obtained by Bunke, Rumpf, and Schick, which I would like to summarize a bit, because since we have this arrow, and from our general picture, we can always go here. All these results apply now to our setting. That's nice. So for example, the first result I wanted to mention is that T-duals are not unique. So this is a very interesting thing that cannot be observed from the Buscher rules. The Buscher rules just are equations that express the data of the left-hand side, of the dual side, by the data of the right.
Excuse me, I'm sorry to interrupt, but I would like to remind you that it is 4 o'clock Warsaw time, so we have to wrap up roughly.
Yeah, no worries. So one of the results is that T-duals are not unique. That also applies to this geometric T-duality, and it requires a kind of change of thinking. We cannot regard T-duality as a transformation on the set of string backgrounds. Also, there are T-duals that don't, there are string backgrounds that don't have T-duals. So there is by no means a map that takes a string background and it gives out another string background. This is inherent topological information. The Buscher rules do not imply that. That's topological thing. And the third thing is that we have this Fourier-Mukai transformation in twisted K-theory, which mathematically is very interesting because it is saying that T-dual manifolds have the same twisted K-theory via this Fourier-Mukai isomorphism. From a physical point of view, it means that the category of D-branes on the two T-dual spaces can be identified in some way, in this way. And all these things upgrade to this geometric T-duality. So finally, I just wanted to point out that one can do this procedure of taking like in general topology, geometric T-duality, locally trivialize that. So we just before did the first layer of this by looking on open subsets, reproducing the old Buscher rules from it. But now one can continue and look at transition data between these local situations. And then we see, for example, from the torus bundles, transition functions, let's call them A, alpha, beta, and from these, from the Kaluza-Klein connection, from the bundle gerbes on these torus bundles, these one forms. So there is local data popping up, and one can evaluate this diagram and this bundle gerbe isomorphism and this stuff also on the double intersections, getting new rules, new Buscher rules, second order Buscher rules for this topologically gluing data of T-duality correspondence. So I just wrote these rules here. They're sort of fairly complicated, I have to say, but that's what one gets when one seeks out the topological information in just the same way that we found out the geometric information on the open subsets namely the Buscher rules itself. All right, so let me skip that, and thank you very much for the attention.
Thank you. Yeah, so I have two quick questions. First of all, I'm still a little puzzled by this constraint that the pullback to U times Tn should be trivial. And
Yes.
my question is, if one follows this approach developed to up to a point, of course, by Krzysztof, following up on earlier works by Kahle and others, right? Where one thinks of T-duality as a construction. That is, one starts with this toroidal background with the gerb, pulls it back to the correspondent space and gauges, that is, equips the pullback gerb with an equivariant structure, gauges the original toroidal action. Of course, there are conditions for that. If one does that, does one actually see this constraint that somehow, because I'm trying to understand it, I had the impression that when Krzysztof was doing this, there were no, there were constraints for lifting the action of your original torus to the bitorus bundle, sure, an equivariant action, things like that. But I somehow don't recall this constraint, so I'm trying to wrap my mind around it. So what is it? Does one see it or not?
Yeah, I don't know exactly, because I don't know exactly how this gauging works, but I think that one has to encounter this obstruction at some point. It has to be there because this work of Bunke and Schick, here this result number 2, that T-duals not always exist, that's a mathematical result. So there are obstructions against the existence.
Yeah, but one could, yeah, sure, but one could play this by saying that there are cases in which you don't have an equivariant structure, right? This could be the anomaly.
Yeah, so the precise result is that you look at this Dix-Medoir D class of the bundle gerb, which lives in this degree cohomology of this torus bundle. So here is this Dix-Medoir D class of G. And then this cohomology has a filtration. It's this filtration one has also in this Serre spectral sequence if one computes the cohomology of the total space of a principal bundle. So this is filtered. And in the last step, it's just the cohomology of the base. And then there are steps in between. So which filtration steps, which are sometimes called in these F conditions. Or maybe that's it already, like this. Because it's just this 2 steps. And the result of Bunke Schick says that this background here consisting of the manifold M and the gerb G has a T-dual if this class is here in this F2 step. And this, yeah, this means that it's like almost equivariant and descends to the base manifold, but not quite. The step here, the F1 part, that's this step where Mathai Rosenberg proposed to use non-commutative geometry. Then you get this non-commutative torus bundles. And the fully general part, the fully general thing would be, it's not even here, it's here. It's then that I've heard that people have invented something like non-associative geometry to treat that. But this very classical differential geometric T-duality, it only exists if the Dix-Medoir D class is here in this lower part of this filtration. And I don't know how this gauging that Christoph was talking about exactly works, but at some point one has to meet an obstruction like this.
So maybe just one last question from me at least. If one thinks of this T-duality as something that gives you a bibrane, a notion that you came up with together with Schweigert in books, right? Would the corresponding defect be topological? Because I mean, it's natural to expect that if it were to be a duality of string theory, of the loop mechanics, if you will, then it should be a topological effect, right? Can you comment on that, or?
Yeah, I'm afraid I haven't thought about this yet. No, I better not comment on it. Yeah, you're totally right. There should be a defect interpretation of that. But
and a topological one, meaning conserving the Hamiltonians, right?
well, you are the expert on defect lines in classical sigma models. So yeah, I don't know.
Okay, all right, thanks. Are there any other questions? Kahle?
Yeah, may I ask, it's a very different direction. So can you comment a little bit on what happens when you have a non-principal torus bundle?
Yeah.
What happens to your approach? Yeah.
Yeah. So this approach that I was presenting here has the advantage that, no, wait, sorry. Let me say it differently. So there is another approach to T-duality, which I wanted to do here, but skipped, which works over this higher gauge theory. So there is this theorem that has been obtained by like a lot of people working on this. So first of all, there is a higher group, the T-duality 2 group, TD, or crossed module. And that group is manufactured in such a way that the bundles for this 2 group with a certain kind of connection correspond precisely to the things I was talking about. 2 topologically general toroidal string backgrounds with an isomorphism, and that satisfies this Poincare trivializability condition. So this is like a fantastic machinery because it puts all this complicated detailed stuff with forms and conditions into just one sort of admittedly sort of complicated thing, because this is one of these higher categorical bundles, but it's just one thing, and there is like theory to understand that. And so one interesting aspect of that theory is that once we have so packed all this into this notion of a bundle for some 2 group, we can study the automorphisms of this 2 group. That's really interesting. So this is again a 2 group, and it is a group extension or 2 group extension of this split orthogonal group. That makes it interesting because that group appears frequently in the discussion of T-duality, of course. And here it appears because it is like the connected components, the pi 0 von ones of this automorphism 2 group. So there is more interesting things to say about this, for example, also in the relation to its T-folds. But in respect to your question, one thing is interesting, namely this split orthogonal group that has an interesting subgroup, namely the GL and Z, which sits kind of diagonally, like you put a matrix on the first upper block entry and then the matrix to the -1 and the lower, then this embeds. And this sequence splits over the subgroup. So in general, it doesn't split, but over the subgroup, it splits. And this means that we can act, I mean, we have a map from this GLNZ to the automorphisms of TD and can act with that now on the TD principal bundles. That means on the correspondences. And GLNZ is not any group, it's the mapping class group of the torus. And so and then there is a theory to take this semi-direct product here of this TD with this other group, gives a bigger 2 group, and then one can look at the bundles for that and translate back into geometry. And what one gets is probably what you asked for, namely a T-duality for affine torus bundles.
Mm.
They're not torus principal bundles anymore, they're affine torus bundles. So,
right. But in this approach, is it understood how to produce a global version of the Buscher rules? I mean, what happens to the method exactly?
Yeah, I have, in principle, yes, but nobody has worked it out really, I think. So this higher categorical approach and geometry that kind of predicts the global approach. So a T-duality correspondence for affine torus bundles is a 2 bundle for this structure group. And then one has to see in how far one can sort of decompose it into like ordinary geometric structures.
All of the pieces. So
And
this hasn't been done yet.
no, I don't think so.
Okay.
I would be interested in doing it, but didn't have time so far. So we did this similar thing here with Thomas Nikolaus. That was like our main motivation. So SONZ is another subgroup of this. The split orthogonal group is another subgroup, and also the sequence splits. So we can take this semi-direct product, and this we have worked out that one can take it as a replacement for these non-commutative torus bundles of Mathai Rosenberg. And that's very interesting, in particular, if we want to take the metrics and the connection into account, which is in this non-commutative picture, I don't know, difficult, I guess.
Okay, thank you.
Thank you.
Thomas, you wanted to
Yeah, I
ask
have a short question. Has this been generalized to non-abelian T-duality?
Not that I know. This is, of course, also a very interesting thing. Yeah. No, I don't know.
Thank you.
Okay. Are there any further questions?
So let me just say one thing. So the only generalization of that picture that I know is has been done by Seemann in an article where he let me try to say it. So where, yeah, which is, yeah, I think which aims at treating these T-duality in the situation where the that would correspond to this non-associative T-duality. So where the gerbe sort of sits completely in the fibers and has no base direction. I think they have a theory of enlarging this 2 group such that it takes care for those cases too. But non-abelian, no, I don't know. I mean, the torus is really important here in the constructions. For non-abelian, I have no idea what to do.
Okay, thank you.
All right, then thank you, Konrad, for being gentle on us.
Thank you for having me.
Thanks a lot. Thanks for a nice talk, and hope to see you around.
Yeah,
Ciao.
hope to see you.
Thank you.
Thank you very much.
Yep.
Bye-bye.
Okay. Bye-bye.